Hello, welcome to another video with the topic of Arena. And in this particular case, we're going to talk about the output that is produced in Arena version 16.20 and probably future versions. It used to be that Arena generated PDF reports, but now everything is coming into Excel files. This is actually, in my opinion, good, because now the user can decide what to do with the information in terms of running its own statistics, which in the past it could have been cumbersome translating the data from a PDF file into Excel and then from there customize work. So this is the output that is produced. There are several tabs, and we're going to discuss what they have in detail. But let's start with discussing that you may have information from several replications. You may need several replications with the purpose of reducing the correlation between the data associated with the process. You have discrete time statistics by replication, and in this case I only ran one replication, but you may have these repeated several times with the replication column indicating how many which replication the data corresponds to. And this output has the project name. I didn't have a name for the project when the project was run, and then in the model I have two entities and or entity types, and we have the information associated with that entity type. So this is what we would call entity-based statistics, because each entity contributes its own data to the average. For instance, well, let's go into the detail of what we have here. When you see NVA, means non-value added. In Arena you can classify the activities as non-value added or value added activity or delays. If it's representing the transformation of a product, say in a milling machine process, it's supposed to add value to the product. In this case, NVA would be non-value added, just like storing something for a little while until it's the machine is, say, available to process it. If the product needs to wait because it's cooling down, well, that would be the decision of the company to consider that either as value added or non-value added, but that is beyond the scope of this course. We have other time and total time, all of these for entity type 1. Transfer time refers to the time that has been transported either by conveyor, transporter, or route, the amount of time that is needed to take the product from one station to the next one. And then you have the value added time. And if the entities, in this case entity 1, is waiting to be processed at one of the value added stations, that is a waiting time. So if you add, in this particular example, we don't have a non-value added or other time for entity 1. If you add the times for value added, waiting time, and transfer time, these are averages, well, the total average would be the number that you see here. So that is the way that this works. We have the same rows for entity 2, right? And then we know from the perspective of the processes and from the perspective of the queues, we have two queues. One is associated with the transporter, one is associated with the conveyor. It happens in my model that the first queue is associated with the conveyor, and there is no waiting time. Every time that the parts are trying to access the conveyor, the cell is available. On the other hand, in a few times, just for a few moments, some of the entities had to wait for the transporter in the model, and that's why the number is non-zero, but it is very small, meaning that it was just very few instances that happened, very negligible. The time in the process for process 2, we have the time in the process by entity is 0.54. The value added, the actual time in the resource, in the machine, if that's what I wanted to represent, it was 0.467. And the waiting time, waiting for the resource to be available, is 0.0798. And that number is repeated because the time in the queue is exactly the waiting time. So if you add either of these two rows to the value added time, you have the total time in process 2 for entity, for both entities actually, because there is no separation by entity. We have the same set of statistics for process 3, and then the statistics for process 4. Now, those were the averages. Now, each one of these rows comes with a batch means half width. What does this refer to? Well, remember that what we're doing is a sampling process, and knowing the average doesn't give us necessarily the absolute true value because it's just a sample. So if we go back to our knowledge of statistical confidence intervals, these half width refers to the 95% confidence interval half width. So it's only one side of that 95% confidence interval. We know that to obtain the 95% confidence interval, what we would have to do is to the mean, we add or subtract 1.96 times the standard deviation of the sample. In this particular case, that number, 1.96 times the standard deviation, would yield these numbers. So you have, for this third row, 0.0191. That number is 1.96 times the standard deviation of the observed values. So the total time is pretty consistent because the standard deviation is very small and the confidence interval is going to be very, very consistent. You will have other parameters in which you have obtained the standard deviations. If there is no data, then the confidence interval half width would be 0, right? If there is no data. Now, you will have in some instances cases where you will see correlated. The reason why you have correlated is because what happens is the information that you see in the average may be correlated from one entity to the next one, to the next one, to the next one, in the sense that the value of the current observation is very highly correlated with the observation of the previous observation, or maybe the previous and two previous observations, and so on. The ARENA runs this particular set of algorithms to identify when it's correlated. So we don't, when the information is correlated, it means that it's not randomized enough to fully trust the averages. Why do we have correlation? You may ask. Well, let's think about it this way. If entities flow very sparingly, separate one from another, what happens with one entity is not related with what happens to the next entity. But when entities, so to speak, jam the system, the utilization in the resources is very high. What would happen is that if the next entity is taking a lot of time, this entity will also take a lot of time waiting, and probably the next entity will take a lot of time, and also likely the next entity, and so on. Only when a lot of time has passed and there was enough time pass as to some entity later, sometime in the future, comes in, then they may find the system is not as busy. And when this happens, when the utilization is very high, yes, eventually the system should catch up and reduce the queue to 0, because the utilization is not 100% or more. Eventually we'll have to catch, but the correlation from one entity to the other will be longer in terms of the number of entities that have this statistical relation among the amount of weight than if the system is not very much used. Now, the system is not smart to know if that should happen or not. It just runs the statistics of one observation to the next one, to the next one, to the next one, and if there is too much correlation, instead of generating a batch half-width, a confidence interval associated to it, it will give you a flag that says this information is correlated. Look at it with care. In this particular example, all the transfer times are exactly 0.1, and that's why we have all the data that you see is correlated. And how do I know that? Because in the next two columns, we have the minimum observed through all the observations and the maximum observed through all the observations. So, and we see that for the one that is correlated, the minimum and the maximum is the same, meaning that all of them were exactly the same. That's not the case for other observations, in which, for instance, the total time in system for entity 2 is a minimum of 0.72. That's the fastest any entity was able to go through the system, and the maximum length, the maximum time that any entity spent on the system was 3.98 for practical purposes, with an average of 1.66. The total number of observations that we were able to obtain to run these averages is listed in the next column, which is in this case 10,093 entities. Very good. Let's see what else we have to the right. Report. We again have the average, and then we have the confidence interval, and again we obtain the minimum, the maximum values. So it is very, very similar. I guess the only additional information that is not repeated here in the second half of the report is that it is stating that the confidence interval that it's associated to the half-width is 0.95. There is an opportunity to change that number somewhere in the parameters of the running when you run the program, but that would be a more advanced feature at this time. In any case, you can estimate the standard deviation because you have the half-width, and all you have to do is take the half-width divided by 1.96, and that would give you the standard deviation of the sample for that particular variable. So what do we have in the next tab? In the previous one, we were measuring the value that each one of the entities contributed to the statistics. In this case, we have the average number of entities that each period of time contributes to the statistics. So we're counting entities here. So for instance, in enter one station, the average number of entities in that particular station was 0.099, and we cannot obtain the mean because it's correlated, and actually what we have is the minimum is 0 and the maximum is 2. Why? Because at some particular point, maybe at the beginning, the two entities enter and happen to be at the same time, but the rest of the time it was, since there is no time at the entity in the original model, that station really doesn't take any time, then it's saying correlated. It's just that station is just used to generate the entities and tag the attributes as needed. WIP is work in process. This would tell you the total number of entities that you have. You have separated for entity 1 and entity 2, so you can know that on average there were 1.89 entity type 1 in the system and 1.68 1.8 entity type 2 in the system, with also you have your half-width for the confidence interval. You will see also that you have a minimum and a maximum. This is the maximum number observed of WIP, work in process, at any given time in the simulation was 11 for entity type 1 and 12 for entity type 2. Both cases were 0, particularly at the beginning of the simulation it was 0. And since the utilization was also less than 1, it may be that at some point the system didn't have any one of particular entities, either 1 or 2. Notice also that if the average is 1.89 and the confidence half-width is 0.03, the total value for the maximum value of the mean confidence interval would be around at most 1.92. What is that number, 1.92? What is the number that I'm computing? I'm adding 1.89 plus 0.0353 because what we're trying to estimate the upper limit of the confidence interval. What is that upper limit? Telling us that we could say with 95% confidence, based on our statistical knowledge, that the mean would be at most 1.92. But in practice, the worst case situation, not an average, but a particular point, we had 11 entities at the same time for entity type 1. Similarly, for entity type 2, the average total is 1.68. The confidence interval for the average is about the maximum, the upper limit, 95% confidence interval, upper limit for the average WIP of entity type 2 would be the summation of 1.68 and 0.044, which is roughly speaking 1.724. And that number is the upper limit on the mean, given that it's a sampling process, but actually in the observed behavior, it may not be very likely, but with our observations, we had a maximum of 12 entities at some point. This counts the number of entities waiting on average. At leave 1, there was none, and it says insufficient as opposed to uncorrelated, and it's supposed to correlate it. And what this means is that simply by the time spent in there, as I mentioned, was 0, and because the time spent there was 0, there is no way to compute per unit of time. Simply, in other words, there was no time spent there at all. The time waiting in leave 2 queue and process 2 queue, the queues associated with the leaving, waiting for the transporters, or the conveyors, which are associated with the leaves, and the processes associated with the actual transformation of the product are listed here, and these are the waiting times and the corresponding not waiting time, but number of units waiting, and the confidence interval to know how many units are waiting, right? And here we see the worst case scenario. For process 2Q, the maximum number of entities observed was 10. The maximum number of entities observed in process 3Q was 7. And the maximum number of entities observed in process 4Q is 3. And the last recorded value is showing 0, meaning that no entities were waiting. We can estimate the instantaneous utilization. This is total time busy divided by total time available, and the number is 0.46. For resource 1, number busy is 0.93. Now, from these, we know that just by looking at these two numbers and assuming that there is no failure in the system, failure of the resources in machines represented in the simulation, we know that this number is twice as that. So that means that if the number of bees is 0.93 on average and the utilization is 0.46, it means that we have two servers, right? So we can see that also here when we compare the utilization. At one point it was 0 when neither of the two were busy, and at some point the instantaneous utilization was 100%, which means that both were used. Now if that's the utilization, which is just a percentage, but the number busy the minimum value was 0, but at some times during the system run, we saw the maximum number of observed resources, machine A or B, was 2 of them. The total schedule is we had 2 as a minimum. The maximum was 2. That is how many we have considered available. There is no failures. The average is 2, and therefore the data is insufficient to generate a confidence interval. Again, the system is not smart enough to know, well, we don't care about that. It's just going to generate, based on the algorithms, what should be either the number or correlated or insufficient. And the same nature of statistics you can find for resource 2 and resource 3, and that pretty much describes most of the information you can obtain. Reports. This is repeated in several ways, and you can filter them and you can explore the data. But for purposes of what we need in this course, this should be enough. So I hope you find this video interesting or useful. If you have questions, you know what to do. Get in touch with me anytime. I'll be happy to answer your questions, and I'll see you in the next video.